Hello, my name is Zachary Hedges, and this is my Physics 2 Lab 4 presentation on bar magnets. The purpose of this lab was to use a phone magnetometer to measure the magnetic field of a bar magnet, calculate its magnetic dipole moment, and see how the field changes with distance. We looked at both on-axis and off-axis measurements and compared our experimental results to a theoretical model. From our data, we found that the magnetic field followed a power law with an exponent of about negative 2.486, and we calculated a dipole moment of about 5.95 amp meters squared. There are three main equations behind this lab. First is the PHYS law, which tells us how currents create magnetic fields. It depends on the current, the constant mu naught, and the position relative to the current. It uses a cross product, which means the magnetic field is perpendicular to both the direction of the current and the direction to the point you're measuring. Next is the magnetic field of a dipole. In this equation, mu naught is a constant, the mu vector is the magnetic dipole moment vector, r hat is a unit vector pointing away from the magnet, and r is a distance. There's a dot product in the equation, which tells us how aligned the dipole is with the direction we're measuring, and that affects the field. Finally, we use the distance dependence formula, d equals k r to the n. We take the natural log of both sides to linearize it, so ln of b equals n ln of r plus ln of k. This makes it a straight line so we can easily find the slope and intercept from our data. For the experiment, we used a phone magnetometer app to measure the magnetic field. We found the location of the magnetometer in the phone and measured distance from that point. We also aligned the phone with Earth's magnetic field so we could isolate it and subtract it later. Then we moved the magnet closer and farther away and recorded magnetic field values for both on-axis and off-axis positions. The system was the bar magnet and everything else was the surroundings. For the on-axis data, we plotted the natural log of the magnetic field versus the natural log of distance. This gave a straight line where the slope is the exponent n and the intercept gives ln of k. From our graph, we got n equals negative 2.486 and ln of k equals negative 13.645. We then related our experimental equation, k r to the n, to the dipole equation and solved for the dipole moment. This gave us a slope of about 5.95 amp meters squared. Since the theoretical slope should be negative 3, our value being less negative means the field didn't fall off as quickly as expected, which leads to an overestimate of the dipole moment. For the off-axis data, we measured all three components of the magnetic field. We corrected the y component by subtracting Earth's magnetic field. After correction, the y values were close to 0, which is what we expect since the dipole field should mostly lie in the xz plane. We then measured the net magnetic field using all three components. Overall, the behavior matched what we expect from a dipole, though there was some variation due to experimental error. We also compared our results to a computational model based on the dipole field equation. The model assumes a perfect dipole in ideal conditions, so it doesn't exactly match, but the overall trend is similar. There were several sources of error in our experiment. These include uncertainty in the exact location of the phone's magnetometer, small errors in distance measurements, and interference from nearby objects. Alignment is also important. If the phone isn't perfectly aligned with the Earth's field, that can affect the results. And finally, the magnet isn't a perfect dipole, especially at close distances. In conclusion, we found the magnetic field decreases with distance in a way that's close to the expected inverse cube relationship. Our calculated dipole moment of 5.95 amp meters squared is reasonable but likely overestimated due to experimental limitations. Overall, the experiment supports the dipole model, even though the data doesn't perfectly match theory. And to answer the what-if questions, if we hadn't oriented our experiment to compensate for magnetic north and had instead laid out the meter stick at some intermediate angle with respect to Earth's magnetic field, how the results have changed. Earth's magnetic field would have interfered with the bar magnets, causing skewed results. And what if you were just stick two identical magnets together end to end and run this experiment again? How would you expect your measurements to differ? The direction would stay the same, but magnitude would double. Thank you.